Hello everyone, welcome to the second part of the talk. In the first video, I explained the construction of the monopole Floer homology for three manifolds with toroidal boundary, but there are many problems to address in order to say this group is well-defined. In the second part, I will focus on one particular problem, the triviality of point-like solutions, and explain why Landau-Ginzburg models are useful for the proof. And we can start to see the connection with some modern symplectic topology. So let's start with the basic definition of Landau-Ginzburg models. A Landau-Ginzburg model is simply a pair where M is a non-compact complete Kähler manifold. W is a holomorphic function defined on M, and is usually called the superpotential in the literature. We further require the real part of W is a Morse function on M. This is the definition when the dimension of M is finite and when the structural group G is trivial, and we will later generalize this definition. The simplest example is when M is Cn and the superpotential is the sum of squares, then the origin is the unique critical point. The second example is when M is C and the superpotential is a polynomial function. The only requirement is the derivative of W has only simple roots. And here I'm writing down an explicit cubic polynomial. Within this Kähler manifold, there exists a distinguished class of Lagrange submanifolds called thimbles. They are simply stable submanifolds associated to critical points of the superpotential. You can imagine this superpotential is in fact a projection map from M onto the complex plane C. And this is a genuine fibration away from critical points of the superpotential. In this picture, each red star represents a critical point, and each red dot downstairs represents a critical value. A thimble is simply the stable submanifold associated to this critical point, and its projection onto the complex plane is simply an array emanating from this critical value. The upshot is a thimble is always a Lagrange submanifold. In particular, its dimension is always half of the dimension of the total space. Thimbles are important because they generate the Foucault category of this Kähler manifold. Foucault category is usually defined by studying Lagrangian Floer homology. So let's consider a pair of Lagrangian submanifolds inside this Kähler manifold. Then their Lagrangian Floer homology is defined by studying the Floer equation, which is simply the Cauchy-Riemann equation defined on this infinite strip R across an interval. And we have Lagrangian boundary conditions when S is 0 and when S is 1. This setup is good enough for many finite dimensional applications. But when the dimension of M is infinite, this Lagrangian boundary value problem is not very convenient to work with. So one may ask, can we define this Lagrangian Floer homology without actually referring to this boundary condition? This question sounds very awkward, but this can be partly accomplished when the second Lagrangian L1 is our thimble. And there are two major modifications of this setup. The first is we wish to perturb this Cauchy-Riemann equation using the imaginary part of the superpotential. And the second modification is instead of this infinite strip, we will consider this perturbed equation on the upper F plane. And instead of this boundary condition when S is 1, we have this boundary condition at infinity. So here for any time t, we want this limit as S goes to infinity to be our critical point Q. And we want this convergence to be uniform in time. At this point, you may ask why these two formalisms are supposed to produce the same Floer homology groups. Let me try to provide some heuristics here. In general, you can perturb this Floer equation using any Hamiltonian function on the Kähler manifold. But when it is the imaginary part of a holomorphic function, this equation carries much more symmetry. Because lambda h in this case is also J of lambda L. J is the complex structure on M. This means the gradient vector field of the imaginary part is also the Hamiltonian vector field of the real part. In particular, if we assume our solution is time independent, So here the time derivative is identically 0. Then this Floer equation will imply the spatial derivative plus lambda L is 0. This means if you go upwards along this red arrow, this is a part of the negative gradient flow line of the real part. But note that the endpoint here lies in the stable thimble. This means that somehow you can continue this flow as s goes to infinity until we reached our critical point Q. This argument at least shows these two Floer groups are generated by the same set of solutions. And the hope is they should also produce the same Floer homology groups. I don't really have a proof for this statement, but this heuristic looks very promising. The second formalism here is the towing model for our monopole Floer homology. In the infinite dimensional case, we'll just take the second one as the definition because the first one doesn't make sense anymore. However, there is one potential compactness issue related to the second formalism, which I wish to explain in more detail. To this end, I have to introduce the energy density function. So let's work with this upper half plane model. Then the energy density function associated to such a solution is a function defined on the upper half plane. And it's simply defined as a sum of a few L2 terms. So here we see the derivatives of P and the square of lambda h. And this density function has two important properties. First, this function u is not really integrable on the upper half plane, but it's always integrable on any finite time interval across this half real line. And you can check this fact by thinking about time-independent solution. The second property is if we know this function is identically 0 on some bounded open subset omega, then this will imply our solution P is in fact a constant map taking value at some critical point of the superpotential. So this density function has a very concrete geometric meaning. Over any bounded open subset, it is measuring the L12 distance between our solution P and such a constant map. The compactness problem will then arise if we consider a sequence of solutions Pi. In this picture here, I'm drawing the profile for their density functions. The problem is, although each function ui is required to decay to 0 as s goes to infinity, this convergence may not be uniform in this sequence. Then some amount of energy may slide off along the spatial direction and converge to a non-trivial solution P infinity on the complex plane. This limit P infinity is subject to the same perturbed Floer equation, and the boundary condition is its density function will converge to 0 in any direction of the complex plane. And this is a picture for this density function U infinity. And such a solution is usually called a point-like solution in the literature. If such a divergence phenomenon can happen, then we have a serious trouble because they will ruin the classical compactification of the moduli space, and the Floer differential defined in the usual way may not have square equal to 0. So at this point, we really want to rule out non-trivial point-like solutions. In this case, we are pretty lucky because this can be achieved using our Morse condition. Our lemma A here says if our superpotential is Morse, then any such solution, P infinity, is necessarily constant. So this divergence phenomenon will not really happen. In lemma A, instead of this boundary condition at infinity, one can also assume the finiteness of total energy. In this case, these two conditions are more or less equivalent to each other, so it doesn't matter which one we choose. Let's come back to this picture. Using lemma A, you can show that even for a sequence of solutions, their density functions will decay uniformly as s goes to infinity. If we know there is an upper bound for the total drop of the symplectic action functional. After that, you can further improve this uniform convergence into uniform exponential decay. This will eventually allow us to prove the classical compactness theorem and obtain the classical compactification by broken trajectories. So lemma A is apparently the foundation for this upper half-plane model. So this is the story for ordinary lambda principal models. So we have introduced a definition, we have discussed a Floer equation, and we have this triviality result, and we wish to generalize them when the structural group G is non-trivial. In this case, we obtain gauged lambda principal models. A gauged LG model is now a triple, where M is again a complete non-compact Kähler manifold. G is a compact abelian Lie group. This action on M will preserve the Kähler structure. We also want this action to be Hamiltonian, admitting a moment map. We also want this action to be extended to the complexified group, and this complexified action is required to be holomorphic. Our superpotential here is again a holomorphic function on M, but now we require W to be GC invariant. The simplest example is when M is C, G is the circle, GC is C star, and the superpotential is identically 0. Then the moment map is essentially a quadratic function. The subtlety arises when we generalize the Morse condition. For instance, you can ask the real part of the superpotential to be a Morse function on the symplectic quotient. But in practice, this is not a strong condition. And the right replacement is really a notion of stability. I don't plan to tell you the definition here. It's really stated in terms of the GC action, and our example here is not really stable. Our next step is to generalize our Floer equation. In this case, we obtain the gauged weighting equations. It's stated in for a pair where A is a smooth connection on this trivial G bundle on the complex plane, and P is again a smooth map from C into the Kähler manifold. But you should really regard this map as a smooth section of this trivial N bundle over C. So whenever we take derivatives of P, we should really take covariant derivatives with respect to this connection A. So the second equation here is just our Floer equation perturbed by coupled with this connection A. And the first equation here is relating the curvature of A with the moment map. The density function in this case now involves 4 different terms. Here we see the L2 of curvatures, L2 of moment maps, L2 of the covariant derivatives, and L2 of lambda h. And the total energy is defined as the integral of U over the whole space. So let's think about this. What will happen if this energy is 0? This will imply all these 4 terms are identically 0. In particular, this curvature, our connection is flight. So up to gauge, A is the trivial connection, and this smooth map P is constant, taking value at the fiber of the moment map and the critical locus of the superpotential. So the trivial solution has a very concrete geometric meaning. Now we have a system of equations on C, and we have a notion of energy, and we can ask the same question as before. Can we find a non-trivial point-like solutions on the complex plane? This question is addressed in lemma A prime, which says if we know our gauged LG model is stable, then any finite energy solution to the gauged weighting equations is necessarily gauge equivalent to a constant solution with trivial energy. So this lemma is saying there are no non-trivial solutions. And this triviality result relies heavily on the stability condition. So let's come back to this non-stable example when M is C and G is the circle. In this case, the gauged LG model, the gauged weighting equations will recover the vortex equation studied by Professor Pavs back to 40 years ago. So in this system, A is a U1 connection on C, and P is a holomorphic, is a complex valued function. The second equation here is simply saying P is holomorphic with respect to this connection. Then this theorem of Top says this vortex modular space is homeomorphic to this union of symmetric product of the complex plane. Here n is a non-negative integer, is also called a vortex number. It's also the number of zeros of this holomorphic section. Basically, Top's theorem is saying for any endpoints on the complex plane, you can construct a unique vortex solution such that this holomorphic section vanishes precisely at this point. In this case, we do have a pretty interesting moduli space, and this means this stability condition is essential in our lemma. Finally, we wish to generalize this story to the infinite dimensional case, and we can see the connection with Seiberg-Witten equations. Such a connection is provided by our lemma B, and here we will allow the dimension m to be infinite. Here we take sigma to be a 2 torus equipped with an arbitrary Riemannian metric, and lambda is a harmonic one form on the surface. Then lemma B says one can construct an infinite dimensional gauge diagonal model such that the Seiberg-Witten equations on this product form manifold perturbed by the standard 2 form is equivalent to the gauge Witten equations on C. Moreover, this gauge diagonal model is stable if and only if this harmonic one form is non-zero. This lemma is saying our Seiberg-Witten equations are not really special. It's just a special instance of gauge Witten equations. Just in case some of the audience might be interested, let me explain the various terms involved in this algae model. We'll start with the trivial line bundle over the surface sigma. And our Kähler manifold M is just an infinite dimensional complex vector space. An element in this Kähler manifold has 3 components. The first component B here is a U1 connection on this line bundle. Phi plus is a smooth section of this bundle L, and phi minus is a smooth 0,1 form on the surface. And the interesting thing is the complex structure is not the standard one. In the first component here, we have the hard star operator, and in the last component, we have minus I. This is the conjugate of the standard complex structure. The superpotential W lambda has 2 components. So for the first component, we apply the d-bar operator of B to phi plus, and then we take the inner product, Hermitian inner product with phi minus, and then integrate over the whole surface. The first component is the Dirac functional. The second term is a perturbation term by this harmonic one form. Here B naught is a reference U1 connection on the trivial line bundle. You can take it to be the trivial differential. And here, then we take the difference between B and B naught and take the Hermitian inner product with lambda. So the outcome is always a complex number. The GC group is the space of mass from the surface into C star. But because this non-standard complex structure, we have to be careful about this GC action. The formula is given by this last line, and alpha is a real valued function on the surface. And in the last entry here, instead of e to the alpha, we have this inverse e to the minus alpha. And this is because this minus sign here. This formula still looks very complicated, but let me mention one interesting property about this gauge diagonal model. When this harmonic one form is non-zero, the critical locus of the superpotential consists of a single free GC orbit, but the superpotential itself is only invariant under that identity component. In this case, the component group of GC is isomorphic to Z squared. This means our lattice vibration is really fibered over a torus, and over the torus, we have a unique singular fiber. Then we pull back this family to the complex plane. So over a complex plane, we have infinitely many critical values for the superpotential. And they form a lattice inside C. They are periodic in 2 directions. And the component group of GC acts transitively on these critical values. I think it would be a very interesting problem to understand the Foucault-Seidel category of this algae model. Finally, we can use lemma b to use the triviality of point-like solutions for the several-Witten monopole equations. This leads to our theorem A double prime. Sigma is again a Riemannian two-torus, lambda is the non-zero harmonic one form on this surface. Then this theorem says any finite energy solutions to the monopole equations on this product four manifold is necessarily gauge equivalent to a constant solution with trivial energy. There are two remarks in order. First, you may wonder what will happen for a heterogeneous case. Indeed, both lemma b and theorem A double prime are still true if we work with the closed Riemann surface with genus at least 2. Lambda is still harmonic, and if the 1,0 part of lambda has precisely 2g minus 2 simple zeros. In this case, we still have a rather interesting gauge LG model. And the second remark is this theorem relies heavily on this stability condition lambda is non-zero. Indeed, interesting solutions can exist if we assume instead lambda is 0, but mu is non-zero. And for the heterogeneous case, there are even more interesting solutions. In fact, we have a complete classification of all point-like solutions. This is done in one of my earlier papers, but still we don't want to work with these solutions. Theorem A double prime is apparently the foundation of our monopole Floer homology. And I can hardly imagine how one may approach this result without knowing the underlying structure of gauged LG model. And this is really the point I want to make for today's talk. So far, we have been using the framework of LG models to understand the analytical properties of the separate Witten equations. But there has been extensive literature in understanding the symplectic nature of LG models, and some of them actually suggest a partial border monopole theory. So in the last part of this talk, let me point out a few future directions and put everything into a broader context. According to Seidel's work, since each London Gizmo model is also a Lefferts vibration, one can construct its Foucault category, and this Foucault category is generated by these symbols. So the long-term goal of this project is to generalize this work to the infinite-dimensional case. In particular, for this infinite-dimensional gauged LG model, we want to construct an infinity algebra. And for any three-manifold Y1 with boundary sigma, we want to construct an infinity right module over A. And for any three-manifold Y2, whose boundary is the orientation reversal, we want to construct an infinity left module over this infinity algebra. In the end, we can glue Y1 and Y2 along their common boundary to obtain a closed oriented three-manifold, and wish to have a gluing theorem to help us recover the Floer homology of this closed three-manifold from this infinity data. I'm not pretty sure what's the statement I want to pursue here, but this gluing theorem should produce a spectral sequence whose E1 page is this tensor product and whose E-infinity page is the Floer homology of this composition. This spectral sequence is inspired by this corollary from Seidel's book. In the first video, we discussed the gluing theorem in the case when sigma is disconnected and when the harmonic 2 for mu is non-vanishing. In this case, one can verify directly this tensor product is isomorphic to the right-hand side, and we didn't really construct the spectral sequence. In the case when the boundary is connected and mu is 0 is much more mysterious. We don't really know too much about this case. This includes the most interesting example of knot complements. For this project, there are at least 3 works I wish to point out at this point. So the study of infinite-dimensional Lefferts vibrations has been pioneered by the work of Andrew Hiddes and Gato Witten. But in their papers, they have a slightly different application in mind. So in their case, this Kähler manifold is a space of SL2C connections on a closed oriented three manifold, and W is the complex value Chern-Simons functional. In this case, the gauged Witten equations will recover the Hiddes Witten equations on this product 5 manifold. And some of the ideas even go back to the seminal paper of Donghao and Thomas, where they consider a complex vector bundle over a copial threefold. In their case, M is the space of D-bar operators on E, and W is the holomorphic Chern-Simons functional. And the gauged weighting equations will recover the spin 7 instanton equations on this product 8 manifold. In some sense, the gauged weighting equations are the universal equation. You can plug in different LG models and obtain different equations in gauge theory. And in their papers, they proposed various ways to construct the Kanasato category for their examples. But none of them actually worked out in practice because of the fundamental compactness issue of their equations. But I think there is a chance to implement their ideas to our monopole equations. So I hope in the future, one can realize this picture and upgrade our Floer homology into this A-infinity categories and prove this gluing result. So this is everything I prepared for the talk. Thank you so much for your attention.